Okay. So we're in week 3. So occasionally you'll still see I still have my old module code in here, like pi0782. I'll try and update that in the future. So you'll still occasionally see old module codes popping up. Last week was all about data visualization, like how to make pretty plots, how to make histograms, how to make violent plots. And today we're going to talk to you about ANOVA. So we're still trying to rehash all the things you sort of know from SPSS, but then showing them how you can implement them into R. So last week we also already covered a little bit of the t-test and the man-with-u test, which are tests you should have had during your undergraduate. So but today's all about ANOVA. So today I'm going to talk to you about ANOVA and its variants, and I'm going to also talk to you a little bit about non-parametric alternatives. You might have seen those to a lesser degree, and you might have not seen some of the alternatives I'm going to be showing you today. And after today, so every single time, after every lecture, you're actually able to complete a chunk of your assignment. So it's really tied into the assignments. And if you haven't done any exercises, some of you are on track and have done all the exercises so far, and I've given you the solutions. But if you haven't done any exercises, now is really the time to ramp it up and start completing those exercises, because you don't want to fall behind too much, because it will pick up and it will become a little bit more advanced as we go along. You'll also notice that as we progress, there'll be more time of me talking and less time of in-class doing type of things, because you should be doing those things on your own during the exercises as well. So we'll shift gears as we progress. So not to scare you too much, but just try to pick up with the exercise if you haven't done any of those just yet. So I'm going to talk to you today about ANOVA, ANCOVA, and MANOVA, and I'm going to talk to you also about some non-parametric alternatives to those tests. So raise your hand if you've never conducted an ANOVA. So you all have done an ANOVA, right? So as part of your bachelor, undergraduate, it's one of the most commonly used designs in psychology. So what you should remember is, like, if we go back to basics, you have variance, and people denote this in different ways. So you can have sigma, S, or variance of X. So depending on which textbook you have, will be one of those. And it's a measure of variability. Yeah, so it's a measure of how much things vary. So you remember, like, you can have a mean with lots of variance around it, or a mean with not a lot of variance around it. Yeah. We also covered some other measures. So can you name another measure of variability that we covered in the earlier weeks? So we covered some other measures to measure how much variation there is in the data. So is there anything that pops out? What? The standard deviation. So that's good. That's going to come next. So because the standard deviation is straight up designed from the variance. So if we take the square root of the variance, we have the standard deviation. We also covered something else. So what's another measure of variability that we covered? The MANOVA is a test across the board. So it's not really a measure of variability. It will be a statistical test using that variability. And it's something which we haven't covered just yet. So we're looking for something from week 1 or week 2. And just to give you a hint, if you think back with the box plot, what does a box plot depict? Okay, you should perhaps go back over your slides, but you might recall the interquartile range. So we calculated the quartiles, we calculated the third quartile and the first quartile, and then we calculated the interquartile range. And those whiskers from that box plot are usually 1.5 times the interquartile range. Yes? So if you go back and look over your slides, those are the other measures of variability which you've seen. So, but we had the standard deviation, which is good. So we can calculate these measures for a sample, but usually the way statistics work is we draw a sample, and we want to make inferences to a statistical population. And so, as you've just pointed out, we also have the standard deviation, and the standard deviation is nothing more than the square root of the variance. And so it's quite common that you calculate means and standard deviations for your reports. So when you do t-tests, so that standard deviation is a measure of variability, of like how much variability there is around these means. But we want to use an ANOVA to compare 2 or more means. So why wouldn't you just do a bunch of t-tests? So any ideas as to why you wouldn't just do like a bunch of t-tests? Because there's just more groups. You could just do another t-test, another t-test, another t-test. So why don't we just do that? Because it seems a lot easier than doing an ANOVA. Any ideas? Want to have a pop? Any ideas what would be the problem if we were to do that thing like just run a bunch of t-tests? You can have a guess, yeah.
Is it type 1 error?
Yes, so we would be doing basically lots of tests, and some of them will be significant. So if you do it like let's say we have 20 groups and we do all these different type of tests, then just by chance one will be statistically significant if you have a 5% significance level. So in order to avoid that type, it's known as multiple testing. So in order to avoid multiple testing, we get type 1 error. So somebody clicked along, so perhaps I should not put the answer straight after it. So, but we could get a lot of type 1 error. So especially if you have a large number of groups, then you run the risk of inflating the likelihood that you find something significant. So that's why we do the ANOVA. So how does it work? Imagine you have a study with 3 groups. So don't be scared, or occasionally there will be some mathematical notations, but you don't need any maths to really get this. You can have 3 means, and they're denoted with x1, x2, x3, and I've used this mathematical notation of this line above to say it's the average, yes? We want to find out if those means significantly differ, and we can calculate the grand mean, which we denote with G, and then we can compare the within, so from those means we can calculate a mean square. So for each of those things we can calculate how much variability there is with the sigma, the variance measure. And we can divide that by 3 in this case, and we can have that within variation, so how much variation is there within each group and between each group. And the premise is that if there's more variation between the groups than within the groups, then we find evidence that the groups are significantly different from each other. Does everybody understand this premise? So the groups will have their variability within, but you can also have between variability between those groups. And if we find more variability between the groups than within the groups, then based on this sums of squares type of method, we find evidence that there is an effect. So don't be too scared. So that's just the premise from it. You can look through all the maths and all the things you've done in your undergraduate. And so the F-test is doing nothing more than comparing the means between sums of squares and the within sums of squares. Yes? And what you then did, if you were really old school like me, you had a textbook with the degrees of freedom. You had a table. You might remember that from year 1 or something. You had a table with T or F values. And you go and look, oh, it has this degrees of freedom. That means this F value is this tail of the distribution. Yeah, that's how you would do it, old school style. So, what are the assumptions of such a test? The dependent has to be interval. You all know what interval means, right? So it needs to be a continuous number. Yeah, so it can't be ordinal or categorical. It has to be a continuous number. We need, as for most things, we need independent observations, and we'll talk more about this when we discuss multi-level assumptions. But we have to make sure that every data point we put into our model, so to speak, or every data point we put into our statistical analysis is independently observed. So if there's some type of hidden clustering, so if one group, for example, was all measured at one school, another group was all measured at another school, or there's a big overlap between school and grouping, then we would erroneously attribute an effect to a group, whereas it's an effect driven by school. Yeah? So we take into account that these observations are made in an independent way. They have to be normally distributed for each category of the independent variable. So within each category, if you take the dependent variable, you should find a nice normal distribution, hopefully. And you should remember a homogeneity of variance. Yeah, so that's something which should ring a bell also. We'll come back to that in a bit. So basically, if there's huge variation between the groups, if they're not comparable, so to speak, if one has a lot of variability and the other one doesn't, and we're comparing apples with oranges, and then some of the assumptions of the ANOVA don't hold. And so that's one of the key assumptions. So we're going to use a new data set, and you can follow along if you're doing it on a computer. So you can go to this this web link, and there will be an SPSS data set. If you go, so that's the web link. And if you go to the SPSS files associated with this manuscript can be downloaded as. So you can download the SPSS dataset just by right-clicking on it and saving it in your working directory. So this is where your SPSS file and your R Markdown script will live. So just right-click and download it. And then you can sort of tag along as we progress. So I'm going to try and show you how to do this type of tests. So you can open the SPSS dataset as follows. You can also open up in SPSS just to have a look at what it looks like. You will find that there's three groups in this data set. There's a group of Asians who are from an international sample. There's a group of people who are Asian Americans, and there's a group of European Americans. And they've all done the NEO-PI-R. That should ring a bell. It's one of the personality measures that you come across for the Big Five. And if you want to find out more, you can click the link for the papers associated with this cell. I sort of set this as my working directory. I call in Haven, and I read in the data like this. So by now, this should be something you've practiced and which sort of feels familiar because we've done it a couple of times in previous lectures. We can look via skim sort of what type of, this is also something which I demonstrated in earlier lectures. We can sort of get a quick overview as to what is available. You can see that we have a character type variable, which is group. That relates to those Asians who are international, European Americans, and Asian Americans. And then you have these, like you have ID, but you also have, this should ring a bell because they're the 5 letters from the Big Five, like agreeableness, conscientiousness, extroversion, neuroticism, and openness to experience. Yeah, so that should ring a bell. And the ID, the clues in the title, that's an ID variable, which should be a unique number, if I'm not mistaken, which relates to the number of the participants. As you can already see, some of these people have missing data. So for 2 groups, we have missing data. So part of what we will have to do also when we work with data sets is clean up the data so we can use them for analyses. Yeah. So what I do, I should put this back in full screen so you don't have a bar. So there's 2 missings which we spotted. We remove this and we need to find out the codings a little bit. So because we only have the numbers attached to it. So what we do is we do data and no miss. Filter, data, group is NaN, and then hopefully we'll have a complete set. Because you could see there's only 2 cases missing, and so you could go back and do skim again. But in this case, you can trust me, it's those, if you remove those cases, then you should have a complete set. And we use print labels to sort of find out what the labels are. So 0 means European Americans, Asian internationals are coded with 1, and Asian Americans are coded with 2. Yes. So what we want to find out now is whether these groups differ whether they differ in openness to experience based on the culture they're from. Yeah, so it's a very basic ANOVA test. And so before we do that, we do the assumption checks. We have, hopefully, if they've done it correctly, we have non-independent observations. There's no real statistical test. So if they collected all the Asians in one school, then that would be a problem, perhaps. But if we read through the paper, hopefully we'll find that they did non-independent observations. There is no real test to discern that. You have to sort of use logic, sort of see if there's hidden clustering in your data, and there will be some other things, pointers, whenever we talk about multi-level models. You can check, if we go back to the numbers, are dependent like openness to experience. Does it behave like an interval variable? Yeah, it has a mean of 95, and it seems to have quite some variability. And you remember that personality scores, they should follow a continuous distribution, right? So you take all the sum scores, or you take a mean, and hopefully that will behave nicely like a continuous variable. So the next step we have to do is like check normality, and then we have to check the homogeneity of variance. Yeah. So we can look back at week 2, how to make a more beautiful plot, but I've just made some basic plots, so you can make all the beautiful plots you want, but for some things you just want to check, and you don't have to make the prettiest plot in order to do that, so you could probably improve on this plot, but you could have a look. And I should specify that most people don't actually look within groups. They don't look whether within Asian Americans or European Americans they find this normal distribution. They just look at the overall distribution of the dependent variable. Yeah. So they look at this overall distribution. So, but ideally, you would check every single group and see if you get a similar type of distribution which sort of looks normal in every group. So what do you think? Does this look okay? Does it look bad? Like, I see you nodding, so I think this looks quite okay. No, it's not too, like you can see some things, but it looks like quite nice, like a normal distribution. I remember from IQ or from height or from some other variables, it looks fairly okay. It's not too bad, I would say. Then you could look at every single thing, and perhaps you could find in this group it's somewhat less well behaved. But you can see overall, perhaps it's not too bad in terms of it being a normal distribution. Yeah. So it's not like we have skew to one side or skew to another side, or completely bimodal data where people only use the extremes. So it's pretty well behaved. So I answered that already, like what do you think in terms of normality? So largely it's okay. And you should remember that you have a central limit theorem to help you. So as your sample size goes up, deviations from normality become less of an issue for your statistical tests. And that's because you can see that if you go back to your central limit theorem, as we start sampling larger and larger samples, we can make stronger and stronger inferences that our tests are in fact robust. And we can do that by simulations if you want to, but basically the premise is the larger the sample, and some statisticians say around 50, some people say around 30, your test statistics will become robust from deviations from normality as your sample size increases. While that doesn't solve the case, like if you have truly ordinal data, like truly categorical data, then this doesn't help you. It's still categorical. So if it's still truly bimodal, then the central limit theorem doesn't help you. So if you just have two categories, yes or no, and you say, oh, I collected 120 cases, so it's fine, we'll use the central limit theorem, that doesn't really work. I'll explain to you further when we get to logistic regression as to why categorical data are slightly different than these type of linear continuous Gaussian data. So what you could do is I think the best thing to do is to check visually as to what it looks like. You could also use statistical tests. Again, some of these things you might have done. You might remember some beasts like Kolmogorov-Smirnov and some other of these normality tests. And so the premise, one of these tests is the Shapiro-Wilk test, and the premise is that this is a test you don't want to be significant. So if it's not significant, you retain the null hypothesis, which is that it's not significantly different from a normal distribution. Yeah, so this is a test you really don't want to be significant. So what we could do is we could filter we can write separate data for all three, but I'll just do it on the first one just to show you. So this is just on Asian Americans, and you find no significant tests on the Shapiro-Wilk test. If we go back and look, where were the Asian Americans? Was it Asian American was 2? So that was, if we go this right-hand panel, so that's perhaps the most extreme case that we have where it doesn't look normal and it doesn't violate this test. Yeah. So if your supervisor wants a statistical test, you can do one. But my advice would always be to check graphically to see what the data looks like and how bad it is. So why is that? I'll come to this in a bit, but some of these tests are easily significant. So as your sample size goes up, you'll have a lot more power to detect even tiny variations in your distribution will then say, oh, it's not normal. So imagine if you're working with 100,000 cases or 1,000 cases, then these tests will become very easily significant, but it doesn't necessarily mean there's a fundamental problem with your data. It will just reach statistical significance easier because you have a large N behind your data. Yeah. So even small digressions in non-normality will then cause it to be significant. So that's why I would always recommend that you sort of plot and see what your data looks like. So we can test it also against a normal distribution, and then you would see that. So this is the Kolmogorov-Smirnov test. I missed this part. So this is the Kolmogorov-Smirnov test, and this is even more easy to be significant than the Shapiro-Wilk test. And this is how you do a Kolmogorov-Smirnov test, which you also had in SPSS. And this is, again, for the Asian population, this is testing against a normal distribution. So you could pit it against other distributions, like Poisson distributions and all sorts of other complex distributions. But this is highly significant. And so if you had taken this test rather than the Shapiro-Wilk test, you would have said, oh, there's huge problems in terms of violations of normality. But as you go back and look, it isn't that bad in the sense that you have quite a large sample, it's quite well behaved, it's not bimodal, you have some skew and some problems with kurtosis, but not massively. Okay. So I should have just specified it's especially the Kolmogorov-Smirnov test which will become easily significant. Any questions so far? Okay, so visual checks. So I recommend that you check your data visually, use histograms, Phi-Lum plots, think back to the data saurus. Like this overall statistical significance test can never really show you what your data looks like. You can have like a correlation or any type of summary statistic, but the actually underlying data might look very different depending on, you could have the same correlation, but again have many different patterns underlying your data. So there's a variety of other options which I'm going to tell you about, which you shouldn't, which you just know that exist. So if you want to toy around, there's all sorts of other ways in which statisticians have devised where you test whether your data is normal or not. Most of this is just for your reference, and you can read from the NORTest package that you have something called the Anderson-Darling test. You have the Kramer-von Mises test. You might remember the Lilliefors correction, which you had for the Kolmogorov-Smirnov test. You have Jarque-Berra tests and adjustments. So there's an abundance of tests where statisticians have looked to see whether data is normal or not. But then my advice would be that you check visually as to what your data looks like. Now the next bit is homogeneity variance. You remember that probably from you remember Levene's tests. I'm also going to tell you a little bit about Bartlett's test. So Bartlett's test assumes normality. So if you have normality in your data, then Bartlett's test is more appropriate. So if that test is significant, so if Bartlett's test is significant, it could also point to deviation normality. So it doesn't have to point to homogeneity variance, but it's a slightly more robust or better used test. So we can test homogeneity variance by this code, so Bartlett.test, and then you remember this is sort of the structure, dependent, independent, the data that we feed to it, and again this is doing, homogeneity variance tests are over the entire data frame, so it's not split by group like we did for normality. Yeah. And you can see in this case it's not significant at p.2, so there is no violation. So Levene's test, so that's also why SPSS picks it, does not make any assumptions about normality. Yeah. So you need a package, you need CAR to do it, and you need to make your data. So you remember this is coded 012, and you need to tell R it's a factor, and so you restructure it as a factor. So that's what I do in the first step, and then the code is Levene test, note the capital, and then you do it like this, and then you get a similar type of conclusion that you have had before. Yeah. So in this case, it doesn't really matter if you pick Bartlett's test or Levene's test. So we're quite lucky. Our assumptions are upheld here. And so if you were to write a report, you would write something like visual inspection suggested that the distribution of a dependent variable is close to normal. So this is referring to this overall distribution. And a Levene's test suggests that the assumption of homogeneity variance is not violated. And then F tests F value, P value. And you remember that APA sort of cares about utilization, like some things have to be italicized like F and P. Yeah? So that means we can move on to the ANOVA. So we've tested our assumptions, and the next thing is we can do an ANOVA. But before we move on, I should mention to you that you could mention that there's kurtosis in the Asian American group. And in your assignment, if you would have said that the Asian Americans are platykurtic, which means sort of a flat, it doesn't have a real peak, yeah? So then I would kind of correct as well as people saying, oh, it's really normal. So some of these things are a little bit of judgment calls, and I'll give you some leeway. But if something is truly bimodal and you say it's normal, then you're not going to get marks in your assessment. Yeah. So there are some things which are quite clear. So you can have a symmetric distribution, a right skewed distribution, a left skewed distribution. This is, if it's normal, then you would have like a normal peak. If you have like a really squashed up peak, that's what statisticians call leptokurtic. And you have platykurtic if it's quite flat. Yeah. So if we go back, then the Asian Americans, their distribution of O looks more like this. Yeah. So you would say it's close to normal, but if any case, there's some indication of platykurtosis if you wanted to be 100% accurate. Any questions so far? Again, these are things which you should know from your intro to stats type things, like what curves look like, etc., etc. So we're going to try and before we move on and do the ANOVA, you're going to try and do the same thing which I just did, but do it for extroversion and use group as an independent variable. So test the assumptions. So that means making this normal plot and making a test for the homogeneity variance. It can be Bartlett's test or Levene's test, where you sort of test the assumptions. Okay, and Alex and I will be around